My name's Eric Lindstrom from NASA headquarters. I'm the program scientist for the Aquarius mission, and I welcome you here this morning for a couple of sessions on the Aquarius results and SMOS results. So this one is entitled Science Results from the Aquarius and SMOS Ocean Salinity Missions, and Gary Lagerlof is going to kick us off with the first talk.
Thank you. Ready to go. Okay, good morning again, everyone. My role is a principal investigator for the Aquarius mission, and the title of my talk is really about introducing you to some of the early results from the first 15 months of data we've collected from this mission. So I'm going to go show you some early results, and then I'll spend a little bit of time talking about the calibration of the data, and then a few comments about what happens next. So this is a picture of our satellite. I think many of you have seen this image before. Why aren't we moving forward? There we go. This is just to quickly remind you about how this mission is designed to sample the ocean salinity. This is a picture of the satellite here. There are three separate feed horns or instruments off this reflecting antenna here. Basically, it makes a footprint on the ground that looks like this, three separate beams. The satellite flies along in its orbit, and we create this swath in what we call a push broom fashion. So basically, there's three beams across the swath. The total width is about 390 kilometers. This is what it would look like over the Pacific Ocean. What the scale of the swath is relative to the ocean and the land, and you can see the track lines of the orbit here. The orbit is here. I'm just going to use this. Is it working? No, I have to do this. All right. 1 second here. Okay. Let me just flip up all these things here so we can just cover all the information at once. The orbit is an exact repeat orbit. We get a global coverage in every 7 days, so we get 4 repeat cycles per month. The basic idea is after we validate the data with buoys and other surface observations that we can create monthly maps with 150-kilometer resolution with 0.2 on the practical salinity scale as the accuracy requirement for monthly average data. This is a map, global map of the first 12 months of data. So this is our first annual average data set from the Aquarius mission. We turned on the instrument in August 2011, so in August 2012 we finished our first year of data collection. You'll see some streaks and stripes on this map. This is a very crude bin average. There's no smoothing, no artificial intelligence applied to this at all. It's just a bin average data set, so it shows all the issues with the data, which is part of what we want to do. It's kind of a diagnostic analysis, so we can see what's going on with the information with the instrument. And now here we are in December. We're beginning our 16th month of data. And our data recovery is very high. It's well over 90%. So in terms of mission success, we're really doing quite well. So what I have here is a little animation. I want to just get this going here. Why are we not getting the mouse? Put this mouse extension cable on here, and it doesn't seem to be working.
Why don't we plug it into
this? Yeah, I'm going to have to do that. Sorry about this. There we go. Okay. Now this is a very time-lapse, high-speed, 1-year animation of the data, and it's going to flip over and keep playing through every year. So in September, it makes a jump between this September and last September. You'll see it jump right there. Okay, so just to train your eye to that. There's lots going on in this picture, and what we see here is a very, very dynamic ocean surface salinity field. What really grabs your attention, of course, is this whole the cycle of the Amazon plume and its outflow and its influence on the tropical salinity in the Atlantic Ocean. But there's a lot happening here in the eastern tropical Pacific. If you look at the Indian Ocean, you see a lot of pulsing east and west, shrinking and growing of the freshwater structure all around the warm pool Indonesian area. You can see things happening in the North Atlantic Ocean. So this is very much a dynamic, rapidly changing, rapidly evolving field that we're seeing with this data. That's really a very interesting, I think, an amazing picture. So I think we're off to some really interesting results that we're going to have as we look at this data over time. A couple of early results, scientific results that have already shown up in the refereed literature. A paper on tropical instability waves by Tony Lee et al. Appeared in GRL earlier this year. We're going to hear more about that in this session later this morning. And then also a paper on the Amazon plume and the influence of hurricanes and the interaction of hurricanes with the Amazon plume is also going to be presented later on in this session. But these papers are already out in GRL. And what's significant about these is that we're seeing much better spatial resolution, higher resolution features in the salinity field than we really ever anticipated with this fairly low resolution instrument that was originally designed to look at basin scale structures. So these results where we're seeing small scale structures was really quite a surprise and the reason why some of these findings were published as early as they were. Okay, those of you who are already familiar with the data, you know where to get it. If you're not, you go to the Aquarius website, aquarius.nasa.gov. Over here on the far right, you see this link for data. This will take you to a data portal at the JPL Physical Oceanography DAC, and there you can download the data files. How many people are registered users for Aquarius data right now? I'm just interested in a show of hands. Okay, most of the people in this room. So. This is just quickly to show you a little bit about the routine data processing and what we have with our browser system at Goddard. The data processing is done at Goddard. So this is just, these are maps of just one day of data, the 28th of November, just last Thursday. So this gives you an idea what the coverage is per day. We have the total, all the orbits on the left column, and then ascending and descending orbits in the two columns in the middle. And as I said earlier, it takes 7 days to cover the globe. So after 7 days, you get a complete map that looks like this. So here you see that combining both orbits together, and here's just one, either the ascending or the descending pass over here. And if you look closely at these maps, you'll see some subtle differences between ascending and descending passes. Ideally, the ocean should be the same, but we're getting somewhat different measurements, and these are part of some of the geophysical errors that we're working on that still have to be corrected in the data. Where we are right now in the processing, those of you who have been using the data are familiar with version 1.3 that's been publicly available since April. We are about to release the next version of the data. We're going to call it version 2.0. It's going to be available by the end of January of this year. These are just two maps of what you get with the existing data set and with one of the predecessors of this new release that we're working on right now. And I'll just highlight a couple of differences here. If you just look inside the circles, you can see some obvious improvements in what's going on with the data, like this anomaly here in the South Pacific was spurious, and it doesn't exist in the new data set. Things are cleaned up around the coastlines, and there are a lot of other features. Many changes have gone into the code. One of the most significant one is that we found about a 1/2 degree pointing offset in the data, and that's been corrected in the new code, and it required us to recalibrate a whole bunch of tables in the processing code, and so that took a lot of time over the summer. And there have been a number of other improvements to the roughness model and other things as well. And Tomas is going to talk a little bit about this in one of the next talks. This is a quick comparison between the data from Aquarius and the Argo data. This is for the first, this is data all the way up until the middle of October of this year, so it's a little bit over a year's worth of data. So this is all the buoy matchups. And what we do here is we plot the Aquarius salinity at the point where it matches up with a buoy. This is just a point comparison. And down here you see the buoy salinity at the same matchup point. And just you can eyeball and tell quite clearly that we're measuring the same phenomenon quite well. Most of the errors you see along the in the Southern Ocean region, the circumpolar current region, where we still have the most RMS difference between the Aquarius and surface observations, and this has to do with both high winds and low sea surface temperatures, which make the salinity retrieval much more difficult. This is just a difference between those two maps that I showed you on the previous slide. And you can see that in the higher latitudes, as I just explained, there's a lot more noise in the differences. Aquarius tends to measure salinities that are slightly less than the buoys in the tropical region. This is why there's more of a blue color here. And this could be partly, at least, be due to a freshening effect of rainfall on the surface, which is going to give a surface measurement from the satellite that's going to be a lower salinity than what the in situ data would be measuring at probably 5 meters depth or so. Okay, these are histograms separating the data out into the 3 different measurement beams that I explained to you earlier. So beam 1, 2, and 3. Generally, the standard deviations for point measurements now, no averaging is being done here. These are just point comparisons, around a half a PSU. We were at over 0.6 PSU with version 1.3 data, so we've definitely improved on things. If you look at the error variance change, this is a reduction in error variance of about 30% from the previous version to the next version of data. Now, we do some screening when we do these comparisons. We're only looking at sea surface temperatures greater than 5 C and wind speeds less than 15 meters per second, so we're not aliasing these statistics with these areas where we know the retrievals are more difficult to get accurately. Okay, one last thing I need to point out here is some of these what we call quasi-monthly calibration transients or drifts, more scientifically called wiggles. And what you see here are the 3 different beams plotted over time, daily average comparison between the retrieved salinity and Argo buoys on a global basis. And you can see these wiggles in the data here, particularly beam 2 is the most conspicuous. And you can also see that the behavior changed sometime about 1/2 to 2/3 of the way through the record, and it became a lot more steady after that. We really don't have a clear idea of what this phenomena is. We believe it's related to the behavior of the instrument, but we don't know specifically what that behavior is or what the root cause of it is. And there's been a lot of debate about how to make corrections for this, because we don't know how much of it to attribute to just the instrument and other problems that we have in the retrieval that correct for geophysical things like the reflection of the galaxy off the sea surface or the roughness or the sea surface temperature and so forth. And it turns out that just within the last couple of weeks, we have worked out a way to separate these issues out, at least to first order, between environmental corrections and instrument corrections. And so we're right now actually implementing those changes to the code. And for that reason, primarily, we've decided to delay the release of the next version of the data until the end of January so that we can make these corrections in the code and do a quality analysis to make sure that the results look good and that we've implemented this code correctly. So this is part of the reason why we're delaying the release of the next data set until the end of January. Now, one last thing I want to show you here is we have this requirement of 0.2 PSU accuracy on a monthly averaging and 150 kilometer averaging timescale. Well, the best comparison point we have for something like this is the data from the recently completed SPURS cruise. This is an ensemble of Aquarius retrievals versus in situ retrievals, plotted as you see clustered here. Most of the data fall within this look like a little square on the distribution curve here. But if you look at the RMS difference between Aquarius and the in situ data average over this month, over this whole area that we were collecting data during SPURS, we're at 0.195 PSU, which is just under the 0.2 accuracy requirement that we have. So my conclusion that I draw from this is that the instrument, the system, the measurement system is clearly capable of meeting the requirement. We don't say that we can do it everywhere on the globe at this point in time because there's still some other geophysical corrections that have to be perfected, but we're obviously well within reach of meeting that requirement. Okay, what's coming next? We have version 2 data release coming up at the end of January, as I said. We have a JGR Ocean special section that's been agreed to with the editors of JGR. Right now, the window for submitting papers is February to April 2012. I'm coming to the conclusion that we should delay that. I would appreciate feedback from any of you about how much of a delay we might need so I can go back to the editors, but I'm thinking probably till after April to start the submission of those papers. Part of the reason why I say that is that we're planning a joint Aquarius SMOS science workshop in April in Ifremer in Brest, France, and I think that the team's got a lot of work to do to get ready for that workshop, and I think it will be the basis for some of these papers that will go into the special issue. So my guess is that we'll push that out until late spring or early summer. If you're interested in this workshop, go to this website and take a look at the agenda. And that's the end of my presentation. And what I can do is put this animation on one more time, and people can look at it while we're answering questions. Or we're out of time. I guess we won't. Okay.
Ask one question.
Okay. Any questions? Okay.
No questions.
Yes, there is. I can't see who.
Tony.
Oh, Tony.
Are you subject to senior review next year, and if so, what are the plans?
Yeah, the question was, are we subject to the senior review next year? The senior review is a process by which NASA evaluates operational missions for going into an extended mission. And the answer is, I've been talking to Cheryl Uhas about that, and the plan is that no, Aquarius will not be in the pool for next review, but it will be in 2015. Okay? And the end of our primary mission is at the end of 2014. So, Seeley. How do I define what? If a buoy is within the footprint that I illustrated in that early slide, when the satellite passes over the buoy within a time window of plus or minus 3 days. Okay? Jacqueline. I didn't hear all that question. I couldn't hear all of it.
You talked about an error on the pointing of the instrument of 0.5 degrees. What was the effect on the salinity? Does it have an effect on the salinity coefficient, or was it an effect on the incidence angle?
Did you understand the question? I still can't hear.
She's asking about a 0.5 degree error in the pointing angle.
Oh, okay. Yes, it changes the incidence angle in the code by a half a degree. We found that there was a pointing error. Then we had to adjust the code to account for that pointing error and set the pointing correctly. And that changed all the retrieval codes because that changed the model function, as you know, is very sensitive to pointing angle. So we had to go back and rederive all the tables and so forth. Okay, does that answer your question? Sort of. Okay. All right, we do have to move on.
Thank you. Our next speaker is Francois Cabot, and speaking on the intercomparison of SMOS and Aquarius brightness temperatures.
So this is the okay. So good morning, everyone. I'm sorry I will not talk about salinity. Really, I will just limit myself to brightness temperature. Because it's more of my expertise.
Could you get a little closer to the mic, Francois?
Yes. Is that better? Yeah, okay. So as an introduction, after the nice presentation of Gary concerning Aquarius, I just want to underline here that we have only currently 2 missions that provide global measurements of L-band brightness temperature, and that would be a pity not to compare them one to the other. Of course, the primary objectives of both missions are using brightness temperature for high-level products such as soil moisture and ocean salinity retrieval, as you know perfectly, but they also are used for other fancy things such as freeze-thaw detection and sea ice thickness and presence assessment. SMOS, as you know, has been orbiting since November 2nd, 2009. It's measuring currently 4 Stokes parameters with a full range of incidence from 0 to 65 degrees. It's a fairly new technology. It's radiometric interferometer. That is, it builds an image every 1.2 seconds in a 2-dimensional image of the surface every 1.2 seconds, and the calibration of the instrument is mainly based on internal noise diodes and an acquisition of deep sky whenever we rotate the satellite to aim at the sky. We have a couple of issues regarding the calibration of the instrument. The first one being the absolute brightness, temperature, accuracy, of course. We want to be as representative as possible as what the surface is emitting. We also need very high temporal stability, and there we have a very specific issue with regard to the way we acquire measurements. It's the short-term stability. We have an instrument which is very highly sensitive to differences in temperature between all the antennas that compose the interferometer. And this cycle throughout the orbit it can be a source of perturbation in the short-term stability. And of course, we want, and this is especially true for soil moisture, we want a very high directional stability. That is, we need to be sure that within the field of view and with the varying incidences, we get the same accuracy in brightness temperature measurements. The data I've been using here is extracted from the first reprocessing data set, which is currently the operational one, which is distributed by ESA. On the other hand, Aquarius has been flying for a bit more than 18 months. It measures 3 Stokes parameters for 3 incidences through a 2.5 meter reflector and feed-on, so it's a very different technology. The calibration was explained by Gary. It's based on internal noise diode and what I call vicarious. It's taking into account the sea surface salinity and the forward model to refine, especially the long-term drift. Of course, I understand also that one of the main issues regarding Aquarius calibration is the beam-to-beam consistency. That is probably harder to assess only through vicarious. And the processing I used is V1.3, of which I understand there are a couple of issues, and I'm quite impatient to see the V2.0. At first, we can, of course, compare global brightness temperature maps. So, of course, this is a comparison that is far too coarse to see any kind of useful information because the conditions are very different, and especially in this example here, I show only ascending orbits, and as you know, SMOS is ascending in the morning, whereas Aquarius is ascending in the afternoon, so we cannot use this kind of comparison. As a method issues, we need to assure that comparison methods must account for basically 3 large kind of issues. One is the geometry of acquisition, and this can be addressed by a careful selection in the SMOS database to find the directional sampling that covers Aquarius incidences. The next one is the footprint and the antenna patterns. So there are 2 ways to take into account the footprint differences. One is to select an homogeneous area, and I will show you one. And the other one is to take advantage of SMOS capability and slightly higher resolution to simulate Aquarius measurements. And the other one is the surface change. Here again, we have 2 solutions for this. One is to select a stable zone, and the other one is to select simultaneous observations, and I will be back on this later on. Talking about stable zone, we have one very good candidate, which is the Antarctica plateau around Dome Concordia, which sits... do I have a mouse? Yes, which is somewhere around here. It's been monitored for some years now to characterize its stability and overall spatial homogeneity. Through ground campaigns, actually, that took place in 2009, 2010, and there is one campaign actually going on as we speak. There is some people down there digging carrots in the ice to monitor the temperature at different depth. And if we extract from our data sets, both for SMOS and Aquarius, all the data that are acquired over Dome Sea, we can draw some very nice comparison, such as this one. So the top plot is what you call the inner beam. It's the incidence at 28 degrees. This is the middle beam, and this is the outer beam. Over the 3 years of SMOS life, these are the red and the green and blue circles for H and V polarization. And from the time where Aquarius kicks in, you have the Aquarius measurements for the same incidence angles. So we can see that despite the fact that, of course, Aquarius shows a much better sensitivity, and so the scattering of the data is far less in Aquarius data than in SMOS, we nevertheless can draw a good conclusion, a good comparison between the two during their common lifespan. Of course, we can start to evaluate that we have small differences between the mean and for H and V polarization, and I will get back on the biases a bit later. The last thing I want to emphasize here is that you can see that each winter, actually, we have a small noisier behavior, and that is well, because of the surface change in the Antarctic plateau that is submitted to wind effects at the surface, and that comes to a small change in the brightness temperature emitted. But if we concentrate on the winter part, we are very, very stable. We can have a look at these measurements in a different way if we plot them as a function of incidence angles. So this is an example of if we take all the SMOS data and we just average them in 1 degree bins and plot them as a function of incidence angle. The dashed line are just polynomial fit and Alley-Kynen model just for reference. We can add to this plot the Aquarius measurements that show, as I said before, slightly warmer TBs at H and V pole. But the directional signature, I would say, is fairly consistent with the one evidenced by SMOS. And we can add on-ground measurements that were made in 2010 by Giovanni Macelloni in the frame of the DOMEX experiment. And we can see that it fits pretty well with the Aquarius measurements for H pole and is a bit warmer than Aquarius for V pole. As far as I understand, if we change 0.5 degrees in the incidence, that should have a very small effect on these measurements. Of course, it can have a major impact on salinity, no problem. But on this comparison, I think the issue is not that much. Okay, very rapidly, I would just to show you some evidence that SMOS is overflying Aquarius about 2 to 4 times every 3 days, thanks to the orbital cycle of both satellites. And over the 440 days that they've been flying together, we collected a bit less than 600 collocation measurements. Of course, all these collocations will occur exactly or around the equator because, as I mentioned before, the ascending and descending passes don't occur at the same time. We put a very simple criteria to define an overfly. It's whenever, as seen from the ground, from the center of one Aquarius beam, to be more accurate, the two satellites are seen within a cone of 2.5 degrees angle. So these co-occurrences appear all around the planet, of course. And we were a bit disappointed to see that the accuracy is much lower than what we can expect what we can get from Dome C measurements. And if we, and beside, it shows a quite different result from what Dome is showing, especially with respect to the bias, because the average bias between is of opposite sign for H pole, and that's a concern, and that we don't really understand. If we refine now the analysis to minimize the difference in azimuth angle, we can see that the thing are starting to look much better and more consistent with Dome C. So probably we have either a problem in the counting of the geometry, which can be a side effect of the pointing accuracy, or we also have small differences that we should be taking into account. Is that the way SMOS and Aquarius are seeing foreign sources, such as the sun, which is of a high impact in the SMOS field of view, or even for the sea surfaces, the way that the galaxy is reflected on the ocean, which is not exactly the same thing because of the azimuth difference. I will have a quick conclusion. So basically, from all these comparisons, we can say that we have probably a small bias between SMOS and Aquarius, between 2 and 5 degrees, depending on the incidence and the surface. The temporal stability is very good in both cases, and that's good for long-term studies. And we certainly have an issue with difference in incidence when we compare SMOS to Aquarius, and our spatial biases within the field of view. The SMOS Aquarius comparison will be continued. We will be moving to the next version. We have for SMOS as well a reprocessing coming in early 2013. With lots of improvement at the level 1, including some improvement in the way we correct for the sun in the field of view. And of course, that will be the next issue to take into account the azimuthal differences. And I think that's all I've got. Yeah.
Thank you very much. I'll let you answer a couple questions while I set up the next one. So, Thomas?
The data for Aquarius that you show, is it version 1.3?
For Aquarius, yes. 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 Yes.
Version 1.3.5, it would just go up because of the antenna pattern. Yeah. You actually get worse.
It will be really valuable to redo this analysis with the next iteration, because one of the things we change is the antenna pattern in the processing code, and that changes the spillover and a lot of other things. We also know that our calibration over the ocean is better than it is over land. Our land is biased because they're further up, separated by about 100 kelvins. So we're not linear all the way across that whole range of, or at least the slope of our calibration curve is not correct over that whole range of brightness temperatures. So comparing over the ice and over the land, I think there's some biases that don't happen over the ocean.
Ice is somewhere between ocean and land, so that's why it can be of interest to both of us.
But we do want to make sure we have the slope of the calibration curve done correctly
Yes.
in the
Yeah.
long run. It's not there yet.
Okay.
Thank you very much. Our next speaker is Thomas Meisner from Remote Sensing Systems. Will tell us about the Aquarius Level 2 algorithm.
Yeah, thank you. I'm talking about the Aquarius Level 2 algorithm, Salinity retrieval. Our team at Remote Sensing Systems is responsible for providing that algorithm, and we had input also from Gary Lagerlöf and David Levine. Starting out with an overview of the physical basis of the Salinity retrieval algorithm, there are those two curves which I show here for V pole and H pole. And it shows the brightness temperature, assuming you have a flat, specular ocean surface. We have used here the Meissner-Wendt dielectric model and stratifies the sensitivity or the dependence as a function of sea surface temperature. What you see is, first of all, so you get good sensitivity in warm water, whereas at cold water, the curves flatten out and you lose sensitivity. And you also see that the V-pole is better, is more sensitive than the H-pole. The translation is about 1K brightness temperature difference, translates in about 2 PSU salinity. So it gives you a rough idea about, in warm water. In cold water, again, you're losing sensitivity. In order to get there, there are lots of things which have to be done. The curve I showed you was for the specular surface, but there are lots of other signals which come in. There are celestial intrusions from the galaxy, from the sun, from the moon, which go into the instrument or which are reflected at the ocean surface. The cosmic background. Then there's the ionosphere, which causes Faraday rotation. There's the atmosphere. There are intrusions from land also. And important, that's what I'm focusing today, there's also the roughness of the ocean surface, which needs to be taken out before we can do the salinity retrieval. That shows the steps which have to be done, getting from Aquarius counts to salinity. First, there's a calibration algorithm, which also has an RFI filter included. Then we're removing the intrusions from the space, galaxy, sun, moon, cold space. The antenna temperature, gives us antenna temperatures. The antenna pattern correction is then performed. And then we start doing Faraday rotation, getting to the top of the atmosphere brightness temperature, remove the atmospheric contribution, and finally remove the surface roughness effect. And then we can go into the salinity retrieval. So there are also steps have to be done before we, in order to get from radiometer counts to salinity. Again, I'm focusing here, want to focus here on the surface roughness effect. That's one of the major uncertainties in the salinity retrieval. The signal is pretty strong, and so that provides an error in the whole algorithm. Roughly 1 meters per second error in surface wind speed, and associated roughness translates into about half PSU salinity error. The necessary data input for that roughness correction in order to take that out is, of course, the surface wind speed. And it depends now what wind speed you are using. In the very first version, post-launch, which we had about a year ago, we were basically just using NSEP wind speeds for doing that. We have then subsequently, that's done in the current version 1.3 and also in the version which is to be released in January, version 2.0. We have included scatterometer measurements. Aquarius has, as you know, has an L-band scatterometer attached, which provides instantaneous measurements. And we have now proceeded to what I call our remote sensing systems testbed version, which is planned to be released through ADPS post version 2.0 sometime in spring next year. And that uses wind speeds which are actually derived from the scatterometer. And we have shown that it's the HH-pole scatterometer, and if you combine it with the H-pole measurement from the radiometer, gives the best performance for retrieving wind speeds. In addition to the VV-pole scatterometer, which has information on roughness beyond that wind speed, something like wave height, for example. Now, the red lines show you the errors which are associated with that. In the first version, it's about, if you compare with a HICOM salinity field, about 0.65 PSU at a single cycle. It's now reduced to a little bit more than 0.5 PSU, and in that testbed version, we get down to about 0.41 PSU by utilizing the scatterometer. So it's a basic flow of the roughness algorithm for the in order to do that. We first derive a wind speed. I call it Aquarius wind speed, and it uses. It's mainly based on the sigma knot scatterometer HH and the H-pole surface, the H-pole radiometer measurement. We still use NSEP wind speed as background field. We need a first guess climatology, and we also need the Reynolds SST. we derive a wind speed, and then we combine that wind speed with a sigma naught VV, with a VV pole measurement. And that gives us a roughness correction. By doing that, we can do the roughness correction. And the roughness corrected brightness temperatures, we call them TB0, that are the brightest temperatures at a specular surface. They then go into the salinity algorithm. All sort of makes it sense if you look why we use the channels in that way. It's kind of important to point it out. The VV pole is not used in the wind speed because it's mainly or largely sensitive to things which beyond wind speed, and it also has no crosswind sensitivity. If the looking is crosswind, it loses sensitivity. Likewise, the V pole is also not used in the wind speed because it's more prone to salinity. It's more sensitive to salinity, but it's then used in the salinity retrieval itself rather than in the wind speed retrieval. Overview over the roughness correction. The delta E, the emissivity roughness, first part is a isotropic part, which is wind speed dependent for V and H pole. That's the largest correction. And then we have I call it the first order roughness table, which depends on wind speed for one, and then the sigma naught VV measurement that gives some additional information. And then we also add a signal which is the wind direction. Depending on wind direction, you have to also include in the roughness correction. Likewise, the scalerometer measurement itself has to be corrected for its own wind direction signal before you can do that. So we need to have ancillary information on wind direction. Coming now to the performance of the salinity retrieval. That's one single cycle observation, it's about 1.44 seconds. And our ground truth here for that comparison was a HICOM salinity field. The upper curve shows a bias in blue and standard deviation in red as a function of wind speed. And the lower panel, the same thing as a function of SST. As I mentioned, roughly the RMS or RSS between Aquarius and HICOM for temperatures above 5 centigrades and wind speeds below 20 meters per second is about 0.41 PSU with it, improved roughness correction. We have to keep in mind here that the HICOM salinity itself has an error which has been estimated. Gary has done some estimations on that for about 0.3 PSU, so you've got to knock that off in order to make your assessment of the Aquarius salinity. As I mentioned, cold water we're using sensitivity, and that's a problem. So you see some small biases, and you also see increased error in cold water because it blows up, because you lose sensitivity. There might be some small inaccuracy in the model function, and there also antenna pattern issues might be a problem. There could also be undetected sea ice in cold water, which leads to those behaviors. That's a Hoffmöller type diagram of the Aquarius minus HICOM salinity. The x-axis is a orbit number, which is equivalent to time, and I'm showing 14 months of data from September 2011 to October 2012. And the y-axis is the orbital angle. The left panel using just NZEP wind speed, and the right panel using the Aquarius wind speed. You see then doing that reduces the zonal biases, and it also helps with improving the galactic radiation. That's another challenge in the Aquarius salinity retrieval. You have to take out the galactic signal. I've plotted that for comparison at the right-hand side. And you see that actually using the Aquarius salinity does help also improving, at least on average, the galactic radiation. That is monthly averages. The mission requirement is for monthly 150 kilometer, 0.2 PSU. Shows it here as a function, how it's a function of time, and the right panel is a function of latitude. Again, you see at high latitude where the cold water is, you have biases, but in between, we are reaching now on a 1 monthly average that the baseline requirement is, they call it 0.2 PSU, about 0.27, and for 3 monthly average is about 0.25 PSU. And again, that's comparison with HICOM. We've got to keep in mind that we have to knock something off here because the HICOM itself is not the absolute ground truth. Now, before I come to my conclusion, I want to say a couple of words about the wind speed performance. What's that for the Aquarius wind speed? What that slide shows is a wind speed in Aquarius wind speed, the upper panel, just it's a monthly, I think it's January 2012. And then the lower two panels are NSEP, on the left-hand side, I compare the NSEP wind speed. Ground truth is here the WindSat and SSMS wind speed, the closest in time. And you see how that improves when you go to an Aquarius wind speed. The RMS goes down from 1.24 meters per second if compared with the Imager to 0.77 if you use Aquarius. I think I'm skipping over the high wind speed because I'm running out of time. Coming to my conclusion. We have shown that the Aquarian Alba and scalerometer is essential for improved surface roughness correction. It's an instantaneous measurement. It has information that is not contained in the wind speed, such as wave height. And that gives an Aquarius a distinct advantage over, for example, SMOS, which doesn't have a scalerometer. We are getting close to the mission requirements. We have shown that when we do the monthly averages, close to the 0.2 PSU. One major outstanding issue I just want to mention that is RFI, which we still have. There are some RFIs sneaking through even over the ocean, and that's something we are going to address. The wind speed, which is used in the roughness correction, is itself a nice standalone product and has a very good performance if you compare it with WindSat. It's something we are considering to do also for future L-band missions. The processing status, that version which I just showed you is going to be released in spring, sometime in spring 2013. It's post version 2.0 because we still have to work with ADPS to get all the code updates to them. You can, however, have that it's available through remote sensing systems, and if you contact me, we can make the data available. Finally, I want to mention also that it also includes results from the microwave radiometer, which is used for making rain flagging and rain correction. And Joel Scott is giving a poster on that, I think, tomorrow. Yeah, thank you.
Thank you. Time for one question.
What?
The 5-meter salinity on HiCom?
No, I think it's surface, isn't it? It's a surface product. Yeah.
Okay, thank you. Yeah. Yeah, thank you. Oh, hold on, I'll get our next speaker. Wow, you're here.
Thank you very much. That's great.
Introduce yourself. You have the mic.
Okay, I'm Merrick Shrokos from National Oceanography Centre. This is mainly work done by my colleague Chris Banks. So if you want to know any details about what I'm talking about, he's the man to ask rather than me. So our aim is to try and produce, I can't actually read that from here. The aim is to try and produce geophysically relevant, validated level 3 data from SMOS and from Aquarius that we can use together for scientific studies. So we are starting with the level 2 data produced by ESA and the Aquarius level 2 data version 1.3. And we are going to validate it using the Met Office operational data assimilating foam NEMO model. So foam NEMO is quarter-of-degree resolution daily, data that we're using average to 1 degree and monthly means. Foam assimilates Argo data as well as SST, sea surface height and sea ice data, so it's a fairly good comprehensive data assimilation ocean forecasting model. The reason we don't use Argo is that the shallowest salinity data are usually below 5 meters, and also the number of hits you get is quite low, so it's very difficult to make a complete validation of any product that you're producing at level 3 at 1 degree resolution. So our aim is to use the foam data to check what we're doing When we started this, we found that there were some quite significant differences between between SMOS and Aquarius. And with the latest versions of the data we're using, also those differences seem to have improved. So what we're doing is we've got 9 months of common data, September 2011 to May 2012. We use the median sea surface salinity values in 1 degree by 1 degree squares. We use the median to get rid of any problems with potential outliers in salinity. And we separately analyse the ascending and descending passes, because when we first started looking at this a while ago, we did find some significant differences between ascending and descending data. So this is just the details of what we do. ESA SMOS level 2 version 5.50 and Aquarius level 2 version 1.3. We use the SSS where the level true retrieval error, because it's an iterative algorithm, is less than 1. We more than 40 kilometres for land for SMOS. We use the various summary flags to ensure that the retrieval is valid, and then we only calculate results when there are more than 25 observations in the 1 degree by 1 degree box. For Aquarius, you have to reduce that number to 5, because obviously with the 3 beams you get much less data. And for Aquarius, we're using these conditions: SSS between 30 and 40, SST between minus 1.9 and 40, and the wind speed up to 60 meters a second. So we're not using quite as stringent conditions as the previous speakers have used. And then we use flags for the various things like RFI and rain. Just to remind you that SMOS and Aquarius do have this ascending, descending difference, 12-hour difference in time. That's just a reminder of that point. So this is a map for September 2011 for SMOS and Aquarius for ascending and descending. And as you can see, there are quite good agreement in many respects between the various maps that we've got here. And if I just flick through for the 9 months, you can see the changes that are occurring in the global ocean. Oops, go back a minute. Over the global ocean in that period. In particular, for example, if you look in the Pacific, you can see the changes that are related to the end of the La Niña at the end of 2011, beginning of 2012. And these changes are common between the different data sets. Although if you look closely, you can see that there are differences between the various measurements on ascending and descending passes. So this is an attempt to quantify what the differences are in the ascending and descending passes. So this is actually data from September 2010 to October 2012. And this is the ascending descending difference for SMOS and for Aquarius. This is done in latitude bands, daily differences averaged up. And as you can see, the SMOS seem to be fairly consistently biased between ascending and descending, up till some point here, at which point it seems to start to oscillate for reasons which we don't understand. And so Aquarius has got this ascending, descending difference, which is also changing in time. Interestingly, the changes do seem to be similar from this point where the level 1C SMOS processor changed in March 2012. So we've still got these major differences between ascending and descending passes which we can't explain or entirely quantify and take out of the system. So now moving on to the comparison with Foam Nemo. So this is Foam Nemo minus the level 3 sea surface salinity products that we derive from SMOS and Aquarius. And I just flick through the 9 months. You can see that many of the differences are in the coastal areas and around the ice edges and so on, which is what you'd expect. So for most of the time, the differences between the satellite and the model are not that large, and therefore, over most of the world's ocean, you can probably use the data with confidence. And just to make the point, if you try and do the same thing for 1 month, this is just March 2012 as an example, using Argo data, you can see that there's very little you can say from this sort of map. So we tend not to be using Argo directly because it's very difficult to draw any strong conclusions based simply on Argo data. If you now start correlating the various quantities, so this is ascending, descending, SMOS, Aquarius against foam, you can see that the density of data is the color, and you get quite high correlations, and the results are looking reasonable, but there are some areas where there are strange things going on which we haven't quite worked out what the explanations for these are. But overall, we are getting more confidence in the data and think that the results that we're getting are becoming believable. And this is if we do the same thing for weighted means. So if we weight the SMOS averaging by the retrieval error that you get out of the iterative algorithm, you do get a slight improvement, but not a huge amount. And this is comparing Aquarius directly with SMOS. And again, there are differences, but overall, these are we're reasonably confident that we're measuring the same thing, although, again, there are differences between descending and ascending passes. So just to finish off, one of the key points is that if you look at the distance from land, so this is distance from land, so this difference between foam and SMOS in terms of distance from land for ascending and descending passes, you can see that there's an effect of the land because of the way the antenna works on SMOS in terms of the retrievals. And if you flick through the 9 months, you can see there are changes that are occurring over the 9-month period, which we don't fully understand. Oops. So in terms of working with the SMOS data, you have to be careful if you're relatively close to land, first few hundred kilometers. Now, Aquarius has got a correction for the land effect, and we were looking at that and doing the same thing, Aquarius against foam, and ascending and descending, and this is with no land corrections, the purple and black curves, and with land correction, the green and blue curves. And as you can see, there is still an issue, or we seem to think there's an issue near land for Aquarius. Although the correction is being applied, it's not clear that it's completely fixing the problem. So if you go through the 9 months that we've looked at, you can see that, oops, in all cases, there is still an issue with the correction. You seem to be overcorrecting near the land. So, to conclude, I got through that rather quick. Both SMOS and Aquarius are producing useful data, and I think these can now be used for scientific studies with care, bearing in mind some of the issues that still remain. Both SMOS and Aquarius show time-varying biases between ascending and descending passes, some of which is probably geophysical, but there could be other issues to do with processing, which we can't quite work out at the moment. And now the SMOS and Aquarius differences that we see due to the processing, the ancillary data that's being used, or to some other factors which we're not sure about. So our conclusion is that we still need to do more work on this, and I'd like to finish at that point. Thank you very much.
Thomas?
Yeah, just two short comments. We showed a big bump in the ascending, descending, I think around May.
Yep.
That's most likely the galaxy, which gets the galactic radiation, which gets strong in May. And then the overcorrection in land in Aquarius, that's something which should be taken care of in the new Aquarius version.
Yeah.
Again, it shows some light.
Yeah. Oh, sorry. I mean, that's true in some of this, but there are some other things going on here apart from just the galactic, I think. I mean, the fact that there's something going on here in the SMOS and then changes, which I don't understand. I mean, why aren't we seeing some variability before that? I'd like to be entirely confident it's that simple, but I'm not convinced that it's that simple.
Jacqueline?
Yes, just to comment here, the bias correction of SMOS is not the same when looking at the retrostate data than the real-time data for 2012. There is only real-time data, and we know that the bias correction is not very accurate, especially when the bias varies very rapidly. And at the very last day, the bias varies very rapidly, so real-time is corrected using the data taken 2 weeks or 1 month before, and this is partly the reason why in 2012 the bias is high.
Okay.
One last question, Gary?
Yeah, Merritt, if you back up, you had some maps where you compared Aquarius and SMOS after these ones here.
Yeah.
I don't understand why you have so many data dropouts in the northern hemisphere in these maps, because you say you use much more liberal filtering in terms of accepting what data goes into your objective analysis. So
Yeah. Well, it's not an objective analysis. I'm not We don't have that many data dropouts. I think if you look at these ones, they're not too bad. I think it's the last one that's the one that's particularly bad. I'm not sure why that one particularly is bad. So I'd have to go back and ask Chris. I'm not entirely sure why that is. But I think overall, if you go to the earlier ones, we don't have the same degree of problem. So I think there may be something peculiar about that month. I'm not quite sure why that is. I don't see that. I don't think it's a major issue. Yeah.
Thank you, Merritt.
Thank you.
Our next speaker is Simon Yue from JPL on the Aquarius wind and sea surface salinity retrieved using the combined active-passive algorithm.
Okay, how can I control the graph? This one?
Yes.
Okay.
I love this.
Real mouse. I love real thing. Okay. So I'm going to present to you the result from an algorithm that has been developed at JPL for the roughness correction, and essentially that will also be very useful for the wind and salinity retrieval together. And thanks to a lot of speakers before me, has already given you a lot of background so that I can skip all those charts. But the bottom line is very simple. The radiometer vertical polarization, horizontal polarization, radar signal 0, VV, and HH. It turned out they all carry different type of information. Some has more dependence on the wind direction, some has more dependence on the wind speed, and the vertical polarization point temperature has more dependence on the salinity. It's quite interesting when you take all of them together, because each one of them has a different emphasis on different parameter. And so therefore, the bottom line, it makes it possible to decouple the effect of that. Okay, and so what we have done is we took those 4 measurements, and then we developed what we call the modeling coefficient based on the data available, and by matching up the crystal data with the NSAP wind, SSMI wind, rain, NOAA wave watch 3 wave height, and so on. And so we figure out the modeling coefficient in the multi-dimensional space. And so once we got that, it's become very straightforward, and you can formulate this kind of a cost function with contribution by the radiometer, contribution by the scatometer, and because of different dependence on the different parameters that I described earlier, so then that will allow us to retrieve the salinity, wind speed, and also the wind direction together. And the algorithm has already been published at the beginning of this year. And since then, we have extended what we have published kind of like early this year to include the effect of the wave. And we also accounted, in fact, we also have done one more study to look into the effect of the rain. And that will be presented in a poster paper this afternoon. I welcome you to stop by. I'll be there to tell you what we have done on the rain correction. Okay. And so this one shows you the wind speed retrieval from this algorithm weekly, and the salinity retrieval weekly. And this is the boiling temperature of the Aquarius overland. Okay. So just to show the Aquarius is able to provide you the simultaneous wind speed and salinity product at essentially the same time. So I'll go into the land portion much later. Okay. Another thing that we have looked at in comparison is to look at the radar measurement alone and to see what it can do for the wind speed retrieval. And again, it's a very simple formulation, very standard cost function type of least square type of thing. So using a VV and HH only. And the result turned out to be something like this. In terms of comparison of this scatometer only, HH and VV combination, and wind speed retrieval in comparison with the SSMI wind speed, you can see this kind of a very, very correlated scatter pattern. And this is what I call the CAP, the combined active and passive algorithm that will be able to provide you. Definitely give you a better result in terms of scatter in comparison with the VV and HH alone. So this one, I think, support what I tell you earlier. If you take all the information together, definitely you can get the more information out of the data itself. And so we also did an error analysis to try to kind of like assess the accuracy of the kind of product. And the upper panel show you the triple collocation analysis that we have done using the V1.3.5 data set. And triple collocation require 3 different independent data set. And so the Aquarius scatometer wind speed using scatometer data only, we are able to get the about 0.9 meter per second on average type of accuracy. And with a combined algorithm, passive and active passive algorithm, we are able to achieve about 0.8 meter per second. And when we use the data earlier from the first few months of the data, in fact, we were able to get about 0.75. And I think there was still probably some kind of calibration issue that we need to work on. And I think once we improve that, I think we can improve the scatometer wind speed a little further, probably even down to about 0.7 meter type of range. Okay. And I told you earlier, we can also get the wind direction retrieval. And so this is what we have done. And so we show compare the wind direction retrieval, and in terms of standard deviation with respect to NSAT wind direction versus NSAT wind speed. And for wind speed under, let's say, 8 meters per second, the radar and radio signal in terms of dependence on the wind direction is really small, so therefore there's really not much skill. But about 10 meters per second, the Aquarius both a radio and radar that has some kind of wind direction dependence. So we are able to get about even 10 to 15 degree type of direction out of that. And in fact, this is part of the reason we are also getting the Salinity retrieval improvement, because we are getting a better wind direction estimate than what the NSAT is able to provide. Okay, this chart shows you the comparison of this algorithm in terms of wind speed retrieval in comparison with the H-wing for Hurricane Katia, and the agreement is pretty good. And there's a lot of rain, and but either scatometer or this Cape algorithm retrieval that's give you the wind speed through the eye pretty well. We got another case, Sandy, I think 1.5 months ago, and so we also look at that, and for this case we got the collocated I think the wind set of SSMI, SSMI ring ray, and the Aquarius Cape wind speed looks pretty well even when there was rain. We know that when there was rain, passive microwave could not give you the wind speed retrieval, but in this case, L-band Aquarius radiometer scatometer appear to be doing pretty well. Okay, there are a few improvements that we have been made. So in the V1.3.5 product, we look at the bias. The bias has some systematic dependence on the SST and the wind speed, and it bias high in the middle range of SST and bias low for the colder water, and then for the warmer water also has a negative bias. And this is kind of like the standard deviation of different with respect to high count. Okay, so purple is good. Purple is down to about 0.2 PSU. Okay, this is 12 months, 28-day average. And so we made just a hypothesis, made a simple correction by linear combining the Meisen and Frank's directional constant model with a client 3 model. Once we make that simple correction, we mostly take out the bias with respect to the SST. And once we take out the bias, and in fact, there's also a big improvement to the standard deviation. The purple area grow much bigger, even further down to the colder water. So I think that support this kind of correction. I think it's making sense. So so that's another improvement that we have made. The other thing that we have done is we look at the effect of the wave. This is 1.3.5 product. And so the bias, the green is good, okay? And so there are still some systematic bias, though, for the very high wave height, very high wind. And so this is, again, the purple is good. So this is the small error, so about 0.2 PSU for the purple. And we use a NOVA WaveWatch 3 product, and then once we introduce that, it turns out the result is also positive. We also improved the bias for many areas. And there was some overcorrection here, but overall the standard deviation also has been improved by quite a bit, so become more purple. Purple is good. Okay, and so once we have taken out the kind of wave effect, SST effect, then we look at the overall bias against the high count. Okay, not all the bias being taken out. There are systematic bias between the Aquarius retrieval and with respect to high count. And so what cause that we don't know, and you can probably see some precipitation pattern here. Maybe rain is probably one of the culprit. And the overall global average difference is very small, about 0.00 something PSU. So the overall mean has been a bias being taken out, but then there's still the kind of regional bias. The other thing that we can make comparison is to look at the anomaly, the change over time for every pixel, every 1 degree by 1 degree bin. And in this case, we compare with the high count. For every 28 days, we create a global average, the salinity map in comparison with high count. Then we compute the standard deviation over about a year. And mostly a large portion of the ocean, the standard deviation is less than 0.2. Okay, meaning that the Aquarius are apparently detecting the changes pretty well. And for the high latitude, I think we are not doing that well because of smaller sensitivity to SSS, to salinity for cold water. So there's still some issue, but apparently there's still some issue for the rain. But the global mean is 0.27. That's very good. Okay. And now I'm going to turn around to show you to focus on the Gulf of Bengal. And so this one shows the change of salinity over a year. This one shows the wind speed derived from the Aquarius data also over a year, or a 7-day average. And in conjunction with that, I'm showing you the boiling temperature from the Aquarius over the Indian continent. And when the boiling temperature is low, they show the timing of the Indian monsoon. Okay, so Indian monsoon kick up, and now over the year become, okay. Colder water, right, precipitation will lower the boiling temperature, and that's how it detected. And that's the correlation with the change of salinity in the Gulf of Bengal. Okay, so that's very, very interesting. So the timing appear to correlate with each other, but we look into further about whether the timing are really the same or not. This is the same as what I showed you earlier, except those are kind of like a static monthly, every 28-day map. And sometime about in early June, the salinity roughly reached a maximum. And when does the Indian monsoon start? Roughly about June. So it seems something is off. So what we decided to do, we pick a box in this area, and then we compute the average Aquarius salinity in the box, and also the Argus salinity in the box. And very interestingly, the Argus salinity that shows the kind of seasonal behavior. Okay, but it also shows a very interesting pattern. The salinity, in fact, will continue to rise into the early portion of the monsoon season. And sometime in the middle of monsoon season, then the surface salinity will drop. Okay, and Aquarius has seen a similar type of pattern, except with a stronger amplitude. Maybe Aquarius is looking at the surface. Maybe surface salinity has a bigger response. Okay, that's one possibility. But both of them does show very similar type of seasonal pattern. And I think the biggest incidence is both of them peak roughly about the same time, at about 2 months after the monsoon season start. And when it reached a dip, that was about October. Okay, about 1 month after the monsoon season end. Okay, in summary, from the Aquarius data, we can get very good wind speed. We can also get very good wind direction for high wind. And the Cape wind speed appear to be even pretty good under rainy condition. And the comparison with the Cartier and Hurricane Cartier and the Sandy, they also look pretty reasonable. And then the standard deviation of the anomaly is about 0.27 PSU. Again, the Aquarius requirement, that this is part of the air budget, is a 0.2 PSU monthly, so I think we're approaching that. And the Aquarius data is showing the kind of a season cycle in the Gulf of Bengal, and the delay response appear to correlate very well with in situ data. And finally, we got a rain correction paper that's in the poster paper. And finally, the Aquarius Cape product available on the PODAC website for download. So I encourage you to take a look at that. And the updated product with the SST and wave height correction will be available soon. Thank you.
Thank you, Simon. One question on this delayed response. Could that just be that the surface salinity is due to the runoff rather than the precipitation?
I think you got a pretty good hypothesis. So we're looking into that.
Any other questions?
As a user, would you recommend using the cap salinities as opposed to the regular version?
I would encourage you to look at both because those are two different algorithms. And with the different algorithm has, each one of them has its own strengths and weakness. And so I think if you look at both, probably you can hopefully find the best from both of them.
Okay, thank you very much. We need to move on. The next speaker is Linwood Jones. Okay. Yazan is presenting.
Yes. On Dr. Linwood Jones, I apologize. Due to last-minute circumstances, he couldn't come. I'll be talking about improved sea surface salinity retrieval using the ancillary data for Aquarius roughness correction. This is a brief outline about the presentation. I'm going to start with the objectives. The objective definitely is to improve the Aquarius salinity retrieved using MWR-derived L-band roughness correction. The point is to use the coincidence MWR brightness temperature at the 37 gigahertz and derive using that an L-band XSTB to be used to improve the salinity. So the first step is to tune the CFRSL, which is Central Florida Remote Sensing Lab Ocean Surface Emissivity Model. To do that, we use the Aquarius Level 2 version 1.35 dataset, a dataset from August 2011 till September 2012. This dataset has roughly 4 million points per beam. We input those brightness temperature to the model, and we use the ocean environment parameters such as wind speeds, which is the NSEP wind speeds, NSEP wind direction, SST, and the HICOM salinity. And what we have is the L-band excess brightness temperature. Two plots at the bottom. The left one shows the brightness temperature for VPOL versus NSEP wind speeds. The red line is the Aquarius surface brightness temperature. The blue line is the Aquarius, and the red line is the modeled. This is for sorting SST and salinity. On the right side, the plot shows two sections. The top section is 12 meters per second wind speed, and the bottom section is 8 meters per second wind speeds. The red dots are the measured brightness temperatures for SST equal 280 and SSS 34. The blue line is the modeled brightness temperature. We can see the y-axis is the brightness temperature, the x-axis is the relative wind direction, and there's a big degree of agreement. The second step is to use the MWR 37 gigahertz ocean TBs, input this to the retrieval algorithm to retrieve wind speeds using GDAS wind direction and SST. Use those wind speeds. Later on, we will use those wind speeds to retrieve the L-band roughness correction. To validate our retrieval, we found a collocated data set between the WindSat environmental data record wind speeds, and we did collocation between these two data sets. Two plots at the bottom. The left one shows the even beams. MWR has 8 beams from 1 to 8. all the even beams and the odd beams has been analyzed separately. The y-axis is the MWR wind speeds, bottom axis EDR wind speeds. We can see the 45-degree line. The majority of the points falls within the 45-degree lines. Also for the odd beams, we did the same. We have a good mean, about 0.37 meters, and a good standard deviation, about 1.6 in the even and 1.8 in the odds. This is another validation technique we used is to compare the wind speeds from the MWR with wind speeds from SSMI. This is a 1-week data set that has been earth gridded and smoothened out to generate a wind speed map. And this is an SSMI 1-week wind speed. This is the same week. It's in 20 seconds of October 2011. Well, given the fact that MWR needs 7 days to cover the entire globe, while SMI needs about 2 days, there's difference in the resolution, but we can see there's a good agreement between both wind speeds. The third step is to use the wind speeds from MWR to retrieve the excess L-band excess roughness correction. This work has not been implemented yet. It's a future work due to some calibration validation that still has to be done for the MWR brightness temperatures. At the bottom plot, I plotted the roughness correction for the L-band for V-pole versus the wind speed. For beam number 1 in blue, beam number 2 in red, and beam number 3 in green. I'm sorry. The sea surface salinity retrieval, those are the steps we go through. We use the L-band Aquarius L2 version 1.3.5 surface brightness temperature. We retrieve excess TB due to wind speed. Simply, we subtract the excess TB from the surface brightness temperature to obtain a smooth surface TB. We use this smooth surface TB to retrieve salinity using the same Aquarius salinity retrieval algorithm being used in the Aquarius instrument. Then we compared those retrieved salinity with the baseline L2 data salinity, which is roughness correction used using this spectrometer. This is a plot between the differences between Aquarius roughness corrected TBs minus CFRSL roughness corrected TBs for the 3 beams versus time. The 2 lines show a 0.4 plus minus 0.4 Kelvin, which is the minimum error we should have in the brightness temperature in order to get a 0.2 accuracy in salinity. Those are the mean bend averages for the 3 beams. This next plot, we made a weekly sea surface salinity using the CFR excess roughness correction. The top panel shows the salinity ranges from 30 to 40 for 1 week. The bottom one shows the differences between the Aquarius salinity minus CFR salinity. This is a weekly map. We can see many differences, some of the differences over the equator and high latitudes. Next plot, we did a monthly average for the same data. It's the Aquarius salinity, the CFR salinity and the differences between Aquarius and CFR. We can see that most of the errors have been eliminated for monthly averages. Next plot, we're comparing the Aquarius and the CFR salinity versus the HICOM salinity. So the blue line is simply the HICOM salinity minus CFR salinity. The red line is the HICOM salinity minus the Aquarius salinity. The top is the mean of those points, the mean of the bend averages. we can see that CFRSL and Aquarius, they both behave differently at high wind speeds. They correspond up to probably 15 meters per second. After that, they start diverging in opposite ways. That was versus wind speed. Next plot, I plotted all the differences in salinity for all wind speeds from 10 meters and higher versus the relative wind direction. You can see, again, the lines are the 0.2 and minus 0.2 accuracy. CFRSL, high command CFRSL in blue, high command Aquarius is in red. We can see good agreement, high degree of agreement within this accuracy requirement. To do further analysis, what we did, we used a co-located data set between the inside of buoys and the Aquarius measurements, surface TBs. We applied our roughness correction to those co-located surface brightness temperatures, and we obtained salinity, and we found the differences between the inside of salinity and the CFR salinity. As you can see, most of the differences, they fall within 0.5 and minus 0.5 PSU. There is no dependence on wind speed. Definitely there's sort of high standard deviation. So as a conclusion, there is an ocean roughness correction algorithm has been developed at CFRSL. Initially, we used the GDAS wind speeds and wind direction to find this the roughness correction. In future, we will be using the MWR wind speeds. The roughness correction is compared with the scatometer. Is showing high degree of agreement, especially for all wind speeds below 50 meters per second. After that, they start to diverge. The salinity retrieval compared to HICOM and the buoy are showing good agreement, and we see no dependence on wind speeds for the majority of wind speeds between 0 and 15, up to 20. Also.
Thank you. Questions?
Yes. Answers.
Thomas.
Just a comment. The current roughness correction for the Aquarius is still mainly based on NZ wind speed.
Yes.
The barometer only comes in as an extra leading order effect. Is there a question, have you calculated in standard deviations between yours and ICOM? You only showed biases.
Here? I haven't calculated, no, I have not. No, I only showed biases, you're correct. Correct. This is the thing I should be looking at.
Any other questions? Thank you very much.
You're welcome.
Our next speaker is Benoit Trenchant, who will talk to us about remote sense of surface salinities in the Mercator Ocean system.
Good morning. First, I will thank my colleague from Mercator Ocean.
You have to speak into the microphone.
Okay. From Mercator Ocean and CLS. So it's not very the good title because we start with observing system experiment with Aquarius data. We start with Aquarius for a different reason. I will explain later. But before presenting this observing system experiment, I would like to remind you where are and what are the SSS error in ocean forecasting system. Here I show you the strong link there is between the SSS error and the rainfall flux. On the right side, you see the SSS difference between assimilation using the rain flux from ERA interim and SSS levitus. you see that there is a fresher SSS anomaly in the tropics and a saltier anomaly at mid-latitude. Okay, it's a free run, it's not a data assimilation run. And in both picture, you see similar patterns between SSS anomaly and rainfall flux difference. It's a rainfall flux difference between ERA interim and GPCP. Okay. Next, I want to show you the kind of error we have in operational ocean forecasting system. It's the difference between the analysis and the observation at the in-situ location. It's the Argo. It's for 2 seasons, you know, GFM and GS 2012. You have the mean, which represents the bias we have for 2 seasons. Largest bias and error are located near the river mouth. Okay, sorry for the... in the western and eastern Pacific, along the equator, in the SEC, and where some of the scale is significant in the western boundary current, Gulf Stream, Kuroshio, and so on. Now is the forecast error we can measure with our system for 2 seasons. It's the difference between the analysis and the forecast. So values does not exceed 0.2 PSU, excepted in western boundary currents, in the SEC, in the Zapiola AD. And they can reach 0.5 PSU in certain region, and even more in high runoff, like Gulf of Guinea, here, Bay of Bengal, Amazon, and so on. And mainly in the ITCZ and SPCZ. When we compare Argo and Aquarius in our ocean forecasting system, we see that compare Argo and our system, globally, the bias is very low. Okay, it's slightly too salty in the Eastern Pacific and in the Atlantic. But if you look at difference between Aquarius, you see that it's clearly biased with a predominant zonal pattern. Here. Now we decide to start with Aquarius data for mainly 2 reasons. Because in both data they have problem with RFI, they have problem with latitudinal bias, they have problem with ascending and descending phases, and they have problem for high latitude. But in the Aquarius data, for the CAP algorithm we chose, as you have seen before, there are less incertitude with the surface smoothness if we use the scatterometer. And SSS retrieval used by SMOS use climatology, and we prefer to have the model dynamic of HICOM. But in the future we use SMOS data, but we have to start. So we start with Aquarius. Our ocean forecasting system, just to sum up this system, it's based on the NEMO version 3.1. We use 3 hourly atmospheric forcing from SMWF. We use data assimilation based on a reduced order Kalman filter, NEMSIC. Okay. We have the bias correction from 3D RAW. We assimilate SST, sea level anomaly, and in-situ profile from Coriolis Center. We made 2 simulations, one without assimilate Aquarius data, and the other one with assimilation of data, SSS data. So in order to assimilate this data, we need to have 2 important things. The first one is an appropriate observation operator. This operator is a key point because we have to to have a good innovation in the system, so we compute the observation minus the model forecast equivalent. We made a weekly mean and a spatial mean with, to have a 1 degree of resolution. We have to prescribe the observation error because in this data set there is no prescribed error. So we build an error from the Aquarius error, I mean the Argo minus Aquarius, and we found the best fit we found is a regression. We found that it was a function of SST square, and some distance to the coast to simulate mesoscale and obviously RFI. So it's the kind of error we obtain, and we have error we change with time, obviously. There are larger errors near the coast and in close to the ice and in the Arctic. It's the first results we have. So the left side is the result without data assimilation of SSS, and on the right side you have the result with. So it's the innovation for the SSS. So you can see the mean bias has been removed in particular area along the Pacific in the equator, also in the Bay of Bengal in the Arabian Sea, but also in the Atlantic. So the data assimilation of this SSS does the job, okay? And on the bottom you see the corresponding increment. So it's the increment of SSS we introduce in the system. So if there is a bias in the system, we introduce a bias. But we can see that it's correlated to the innovation. Now it's interesting to see the impact of this assimilation on other variables. Here you see the mean difference between observation and model forecast for the vertical profile of salinity, okay, and for temperature. On the left you have the experiment without data assimilation of SSS, and on the right with assimilation. You see that there is a strengthening of a positive bias near the sea surface. It tends to freshening this surface. There is a lower impact in the subsurface. The model is saltier than observation here. For temperature, there is no important change. Okay, so this simulation come to from September 2001 to April 2012, and it's still running on the computer, but we stop in April. So there is no important change on the temperature profile. Okay, if you look at the error, the RMS difference of the observation and the forecast, you see that there is no important change on the salinity profile and no important change on the temperature profile. If you look at in a particular region, in the South Indian region, you see that the strengthening of a positive bias we see in the global plot is in this region, okay, and the RMS difference is not significantly impacted. The impact we look at the impact on SSS itself. You see the mean and the RMS difference between observation and forecast without and with data assimilation. Globally, if you average this difference over the globe, you see there is no bias. Okay, the innovation is close to zero, and the RMS difference is close to it's the black line, okay, because the orange line is the comparison with the in situ data. So the black line means 0.6 PSU of error. If you look at another region in the Indian Ocean, because there is not many problems, but the main signal in our results come from this region, the Indian Ocean. So if you look at a little region in the Arabian Sea, you see that without data assimilation, we add a large bias, and we reduce this bias by assimilating the Aquarius data. And the RMS difference is not changed. Another impact, maybe it's the most surprising impact, it's on the sea level anomaly. Always on the left you have the data simulation, the simulation without the SSS, and on the right with the SSS. And you see that we reduced the error. It's the innovation of sea level anomaly for this region, in the Gulf Stream region. And we see that we reduce the innovation, and we the assumption of this effect. Maybe it's due to sorry, I forgot to present you the two plot here. Is the time evolution of the sea level anomaly innovation, so observation minus model forecast for three satellites, JSON1, JSON2, and VSAT. So run 1 is without data assimilation, and run 2 is with data assimilation. And you see that for this particular region, we decrease the RMS of difference, but mainly during October, November, December 2011. And it's surprising because when I saw the slide before, apparently there is a different answer with the 3 beams during this period. So, but apparently the best period for sea level anomaly was October, November, December. Okay. And the assumption is that SSS, in fact, improve or bring another constraint at the surface, at the sea surface, okay? Because during this particular week, okay, so it's not October but November. If you look at the cloud cover fraction, you see that there are many clouds in this region, and maybe the SST was a lower quality, and maybe the gradient seen by SSS bring another information and improve indirectly the sea level anomaly. So it helps to constrain the mesoscale pattern in certain region, and we check this effect in several regions. In Agulhas region also there is an effect. In the ACC close to the Agulhas region, there is a positive effect on the sea level anomaly. So to conclude, I sum up the presentation. We show that important bias exist in SSS measured from space. Okay, we can introduce by assimilating this SSS bias in some region, equatorial band. Okay, data assimilation, maybe of this data, is probably not the definitive solution to close the water budget due to this bias. When we assimilate SSS data, we show that we do not disrupt the equilibrium with other data. there's uncharged assimilation diagnostic. Okay, and the best diagnostic we have is the innovation vector. Okay, observation minus model forecast, and we saw that there is any change, not important change, on in situ data, on SSS, SST, and sea level anomaly. So this data may help to a better constraint mesoscale, as we saw just previously. In regions where constraint from other variable is weaker, larger error for SST, for example, to fill in situ, situ data gap, like in Arabian Sea or Bengal or Amazon. So it's a first step. We need to continue with such today to better understand this data, this SSS and the hydrological cycle. In particular, we plan to remove the bias before assimilating this data. Okay, it's really an important issue because you can introduce a large base, seasonal bias. We have to assimilate other data, SMOS data, and combining SMOS and Aquarius, and maybe use L2 data, but we have preferred to use L3 in the first time because maybe it's less noisy than L2 data for our system, and we have to work also on observation errors. Thanks for your attention.
Thank you. I urge you to take up questions during the break.
Okay.
Okay. We have one final talk to fit in here from Jordi Font, and it's a subject that I've been waiting for my entire career, satellite-based TS diagrams. I just can't wait to hear this.
Good morning. So, I'm the co-lead investigator in SMOS for Ocean Salinity, but I am not presenting an overview of the salinity retrieval by SMOS. We have, after the break, we have an invited presentation by Jacqueline Boutin with several results on SMOS salinity. What I'm presented today is mainly the work by Roberto Sabia, that is now with the European Space Agency. So the idea is, if we are able to build reliable TS diagrams coming from satellite measurements. So what I will do here is to present what data sets have been used, in situ data for comparison, and then salinity and temperature retrieved from satellite, what kind of analysis has been done here, and then some results. These are for sure preliminary results, and what could be future lines of investigation with this. So, as I assume all you know, TS diagrams is a very, very classic analysis tool to identify and locate water masses in the ocean. Usually it's used in vertical, but here the idea is how we can do this in the surface ocean using satellite information. So, what I will present here, first we have a sort of a reference data set that is climatology. With this, we build some kind of benchmark TS diagram for comparison to satellite retrieved diagrams. And then we are using here different configurations for this analysis. We use both SMOS and Aquarius, just simply bint level 3 products, and for this we use Ancillary sea surface temperature. And then in a second step we are using optimally analyzed data sets from both the salinity satellites, and for this we use the GERST sea surface temperature. So here is an example of what we will use from satellite. On the left we have SMOS sea surface salinity, just bint level 3 products. On the right, we have the Ancillary SST, and then on the bottom left, we have a combination of both. The background color is salinity, and then the isolines are for sea surface temperature. And then on the right, what we have is a three-dimensional TS diagram. In the horizontal plane, we have salinity and temperature. Then in vertical, we have latitude, and color-coded, this is for longitude. So then, to start working on this, what has been done is to, let's say, cluster the surface water masses. We have identified up to 19 water masses in the surface layer, and these have been grouped in 7 different ocean regions, as they are explained in this map. So, these are the first global TS diagrams. On the top, we have the reference, that is the TS diagram coming from climatology. The color is to code the different regions. And then we have on the left those that have been derived from SMOS, and on the right, derived from Aquarius. If we see the first round, that is when we are just using bint data, together with answer E for sea surface temperature, we see that they look quite reasonably similar to the reference climatology, but for sure, SMOS is much more scattered. While if we go to optimally analyzed products, we see that in this case is Aquarius that presents a higher scattering in the values. For sure, as it can be expected, we have a larger scattering in salinity than in temperature. So if we look at 3 specific regions as an example, we have on the left, we have the Southern Ocean. We see that there are very, well, I have to say that this, what we have in blue, in the upper line, in blue we have the reference, and in red we have the satellite-derived TS diagram. For sure, we have important mismatches in this Southern Ocean, what is not surprising due to the known problems with cold temperatures. In the center, we have the equatorial Pacific, where the results are reasonably good. They agree quite well. And on the right, we have the Southern Atlantic, where we have, again, some discrepancies. I have to say that this is for the case of SMOS for salinity and SMOS bint, as I said before, and Ancillary for sea surface temperature. And then in the bottom, we have another way of examining this, that is to look at the grid point mismatches. So in this kind of diagrams, we indicate the difference between satellite and climatology in temperature in the vertical, and same for salinity in the horizontal. So the disagreement, the mismatches we have seen before, can be also analyzed in this different way. When we have some, let's say, information in this, these kind of mismatches are going to higher temperatures simultaneously to higher salinities or not, etc., etc. These are just examples that have been shown for the 3 different regions with different characteristics. So, and this is a way of trying to derive some kind of indexes for overall mismatches that will be used in the following slides to identify geographically areas of different behavior. So what we have here is this is the same dispersion diagram, point by point, and we define what we call the mismatch radius, is the amount of difference between the satellite and the in situ reference, and then mismatch angle that can allow us to locate if we are going to overestimate or underestimate both salinity and temperature. I have to recall that this is just an analysis of the mismatch between both data sets. For sure, it's not an assessment of the error, because it may happen that we obtain for sure from satellite additional information that is not wrong, but is not existing in the climatology. So what see here is the a geographical distribution of the mismatch radius for the 4 configurations we have used. On the left, we have SMOS. On the right, we have Aquarius. On top, we have the bined products. And at the bottom, we have the optimally analyzed products. So we can see here that with the color, we are cutting this mismatch radius, where we see that we have different regions where they take different values, and these are quite coherent in the 4 configurations. If we look at the mismatch angle, in this case, we are just color coding 4 regions. As you remember, we were going if we are under or for the salinity and temperature, if we are underestimating or overestimating the difference, the difference, I would say. And as you can see, there are significant differences depending on the product we are using, but also with some characteristics that correspond to geographical areas. So it means that in some cases it can mean problems we have in satellite information, but in others it can be just that we are providing some information here that is not present in the climatology. And now what I present here is a new step on this, is when we examine temporal variability. In this case, we have 7 months just using the optimally interpolated configuration. On the left, we have SMOS. On the right, we have Aquarius. As it's easy to see that for sure that there is an important temporal variability. And again, we see, I don't know exactly the reason, but maybe something was not very well done with this optimal interpolation analysis with Aquarius, but we have quite more significant scattering in salinity with Aquarius than with SMOS in this case. So if we examine the same 3 regions as we did before, with the optimal interpolated products, the behavior is much more closer to climatology, but for sure we are obtaining information that it's relevant from the temporal variability point of view. And this is the same for the mismatch radius, evolution in time, on the left for SMOS, on the right for Aquarius. They are relatively similar, but again, if we are looking at the angle, the temporal evolution is really strong, and the behavior is for sure not exactly the same. So, just to finalize, I have to say that this is a first attempt to see if it's important. Well, it's feasible to do this kind of analysis from satellite. And what I'm listing here is that what we pretend to do in the near future. So is try first, instead of comparing to climatology, comparing to Argo optimally interpolated maps to capture the temporal variability in this case. So we will be better placed to identify if satellite is providing additional information with respect to the Argo data. Then we will try using different satellite products. For SMOS, until now, we have used the level 3 products that we are building at the SMOS Barcelona Expert Center. We plan to use also the CATDS, the French production center. We want also to try different sea surface temperature data sets, and for sure doing different ways of identifying the different regions, in this case, using additional information, for example, taking into account biological characteristics. Another aspect is introducing information on density, try to analyze, try to see if we can use other methodologies and other ways of obtaining relevant information from this. At the end, the question is that with this, we plan to see if it's really this method is a valuable tool to identify, for example, some additional information on salinity bases, if we are really able to work with a good identification of water masses, and for sure in general to give some insight on the ocean circulation processes that are buoyancy driven. And I think that is the end. Okay, thank you very much.
Time for a question or two? I'm fascinated by doing this. The classical oceanographer in me loves TS diagrams, and the old-fashioned idea was that, and I've sold Aquarius this way, is that the temperature salinity diagram at the surface is also reflected in the vertical. You know, that water masses get their temperature salinity signal at the surface in winter. So a TS diagram at the equator in the vertical might be equivalent to one from the surface to the pole at the surface. So it's fascinating to try and merge the vertical with the horizontal and really bring the whole depth of the ocean into the picture.
Okay, good.
I would then conclude our session for this morning. Let's have a round of applause for a lot of great presentations. You get exactly 20 minutes for a break, and then we have 2 invited talks following on at 10:20. So really good talks to come. Make it a quick break and come back. Thank you very much. Thank you, Jordy.